Very good morning and warm greetings to everyone. Today we are going to see about the moment area method to determine the slope and deflection of a simply supported beam which will carrying UDL of W per meter run, that is the intensity of UDL throughout the beam section. You know that the case of moment area method, the slope wherever it is required that will be given by theta, it is equal to capital A by EI, where capital E is the area of the Benjamin diagram between the two referred points, and EA is the fluxual rigidity of the beam in kilonewton meter square or Newton to millimeter square. Then to find the deflection of the beam, so we are using the equation of y is equal to, or delta is equal to AX bar divided by EI. You know that where capital A is the area of the Benjamin diagram between the two referred points, and where AX bar is the first moment of area of the free Benjamin diagram between the 2 points where we are going to find the deflection. So this is the general equation to find the slope and deflection in the case of a moment area method, that is moment area theorem 1 and moment area theorem 2. So now simply supported beam of span L, UDL throughout the beam. So therefore the reaction of the support is VA is equal to VB because of symmetrical loading, that is equal to W into L divided by 2, where small w is the load intensity per meter run. Then if you are drawing the Benjamin diagram, so it will come in a parabola, positive one, that is sagging moment, which is of WL square by 8 is the maximum moment, and the curve is a parabolic curve. Then to determine the deflection and the slope of this UDL W per meter run on a simply supported beam, theta A is equal to theta B. Since it is symmetrical, I am taking half of the loading and the bending moment diagram. You can see that A by EA, so that is the slope, where area is the 2/3 of B into H. So 2/3 into L by 2 into WL square by 8. So if you are simplifying it, you are getting WL square by 24. So the slope is theta is equal to WL cube divided by 24 EI. So WL cube by 24 EI, that is the slope at the support A and B. Similarly, if you are finding the deflection at the center or midspan of the beam for a parabolic Benjamin diagram, so slope YC is equal to delta C, that is equal to AX bar by EA. So here AX bar, so you know already A is capital A is equal to WL cube by 24. I am taking divided by EI into X bar is what? So X bar is deflection at C with respect to A. So if you are taking it, it is into, right, 5 by 3 into L by 2. 5 by 3 into L by 2 is the X bar. So if you are simplifying the above equation for the deflection, you are getting YC is equal to delta C, that is equal to maximum deflection at the center is equal to W 5 WL per 4 by 384 EI. It is YC is equal to delta C is equal to 5 WL per 4 by 384 EI, where small w is the unit of the UDL per meter run, it is intensity of UDL per meter run, L is the span of the beam, and EA is the fluxual rigidity of the beam. So this fluxual rigidity can be given directly or If the cross section is given, young smallness of the material of the beam is given, you can find the fluctual rigidity. For example, capital E is equal to 1.5 into 10 power 5 MPa, and cross section of the beam is say 300 mm by 600 mm. I is equal to 300 into 600 cube by 12 in terms of millimeter to the power 4. You substitute all the values in the deflection equation, you can find the deflection. At any case, the deflection, maximum deflection should not be more than the effective span divided by 500 in terms of meter. Thank you very much for patient listening, and God bless. Valka Vayagam, Valka Valamudan. Good morning.